Hi, this is Schwartz from MasterMathMentor.com. This is video Precalc01, and the topic is radians and degree measurement. The first part of precalculus deals with trigonometry. Trigonometry is simply the study of triangle measurement. It is a branch of mathematics that studies relationships between the sides and angles of triangles. The word trigonometry is a 16th century Latin derivative from the Greek words for triangle, trigonon, and measure, metron. An angle simply rotates a ray about its endpoint. So we talk about the initial side and the terminal side of the angle. The initial side is the starting side of the ray, and the terminal side is the ending position of the ray. The vertex is the endpoint of the ray. We can and do draw angles in any position. However, many times we draw angles on the Cartesian plane. And when we do that, we draw them in what is called standard position, where the origin is the vertex and the initial side is the positive x-axis. If the angle is rotated counterclockwise, we call it a positive angle. If the rotation is in a clockwise position, we call it a negative angle. Angles having the same initial and terminal sides are called coterminal angles. For instance, if we do a quarter of a rotation and 1 1/4 rotations, we have performed two very different actions, but the terminal side is the same. So those two angles are called coterminal. The vertices of triangles usually use capital letters. So in Trig, we sometimes refer to angle A or angle M. But when focusing on the angle itself, Greek letters such as alpha, beta, and theta are usually used. Theta is the go-to variable for angles, just as x is the go-to variable in algebra. Most students know that angles are measured in degrees, and that 360 degrees makes up one full rotation of a circle. Why 360? There are a number of theories for this, many revolving around the fact that 360 is approximately the number of days in a year, how long it takes for the Earth to do one revolution about the Sun. Realize, however, that just like length, there are a multitude of ways to represent it. If you are interested in the length of a picture, then inches might be appropriate. If you are interested in the distance between two cities, it is better to use miles. So it will be with measurement of angles. The most important way to measure an angle is using radians. A radian is defined as the central angle of a circle whose arc length is exactly the same as the radius of the circle. As you can see in the picture, we have a circle, we have an angle that is formed by two radii, and the arc length is also the length of the radius. This represents 1 radian. A radian is the arc length of the circle divided by the radius. And because the units of those measurements cancel out, a radian is a pure number, meaning that no units are needed. While sometimes a capital R, or possibly the term RAD, is used, if no units are measured in describing an angle, then it is measured in radians. So the angle theta that you see in the picture would be the arc length r divided by the radius r, and that would be 1 radian, or simply 1. Realizing that 1 radian is the central angle formed by laying the radius of the circle onto the circumference, you can see by the picture that there are exactly 2 pi radians, or about 6.28 radians in one circle. So what is it that you really need to know? As a circle gets traced out by rotating its rays, we have a full circle, or 360 degrees, which can also be written as 2 pi radians, or can also be written as 1 revolution. So 360 degrees is the same as 2 pi radians, which is the same as 1 revolution. And just as we measured different distances in inches or feet or miles, depending upon what we were measuring, we will do the same with angles. Sometimes we will use degrees, sometimes we will be using radians, and others we will be using revolutions. The first thing we need to know is how to convert from one measurement to the other. Many times you are asked to convert an angle from one unit to another unit. In order to do so, we remember the relationship 360 degrees equals 2 pi radians equals 1 revolution. And you will always multiply your angle by the ratio of one of these to the other, which is simply number 1. So to convert 60 degrees to radians, we multiply our 60 degrees by 2 pi over 360 degrees, which again is 1. And when we do our cancellation, we get that 60 degrees is the same as pi over 3 radians. And again, it is not necessary with radians to describe the units. No units always describes radians. Realize that we can also reduce 2 pi over 360 degrees to pi over 180 degrees. When we multiply that by 60 degrees, we still end up with pi over 3. So it's up to you whether you want to use 2 pi over 360 or pi over 180. You will always get the same answer. So to convert 7 pi over 2, which is in radians, to revolutions, we multiply our 7 pi over 2 by the fraction 1 revolution over 2 pi. The pi's cancel, and our answer is 7/4 revolutions. So in A, converting 180 degrees to radians, we multiply 180 degrees by 2 pi over 360 degrees, and we get pi. To convert 180 degrees to revolutions, we multiply the 180 degrees by 1 revolution over 360 degrees, and we get 1/2 of a revolution. In B, we have 30 degrees. To convert that to radians, we multiply it by 2 pi over 360 degrees, and we get pi over 6 radians. To convert 30 degrees to revolutions, we multiply it by 1 revolution over 360 degrees, and we get 1/12 of a revolution. To convert pi over 2 radians to degrees, we multiply pi over 2 times 360 over 2 pi, and we get 90 degrees as the pi's cancel out. To change to revolutions, we could either work with the pi over 2 or we could work with the 90 degrees. Working with the pi over 2, we multiply it by 1 revolution over 2 pi. The pi's cancel and we get 1/4 of a revolution. In changing 3 pi over 4 radians to degrees, we multiply that by 360 degrees over 2 pi, and we get 135 degrees. To convert to revolutions, we multiply 3 pi over 4 times 1 revolution over 2 pi, getting 3/8 of a revolution. In E, we are given 1/8 revolution. We change that to degrees by multiplying 1/8 revolution by 360 degrees over 1 revolution. The revolutions cancel out, and we are left with 45 degrees. To change to radians, we multiply our 1/8 revolution by 2 pi over 1 revolution, getting pi over 4 radians. In F, we are given 2/3 of a revolution. We change to degrees by multiplying that by 360 degrees over 1 revolution, getting 240 degrees. To change to radians, we multiply our 2/3 revolutions by 2 pi over 1 revolution. The revolutions cancel out, and we're left with 4 pi over 3. In G, we are given 225 degrees. To change to radians, we multiply that by 2 pi over 360, and we get 5 pi over 4 radians. To change 225 degrees to revolutions, we multiply by 1 revolution over 360 degrees, getting 5/8 of a revolution. In H, we have 5 pi over 3 radians. To convert that to degrees, we multiply that by 360 degrees over 2 pi, and we get exactly 300 degrees. To change it to revolutions, we multiply our 5 pi over 3 times 1 revolution over 2 pi, and the pi's cancel out, getting 5/6 of a revolution. It should be noted that A through H are all what are called special angles. They are multiples of 30 degrees, 45 degrees, or 60 degrees. And since we will be using them a lot, you will end up actually memorizing these without actually intending to, as we will always need to convert from one to the other. I, 11/15 revolutions, is not a special angle. We multiply it by 360 degrees over 1 revolution, and we get that it's exactly 264 degrees. To change to radians, multiply it by 2 pi over 1 revolution. The revolutions cancel, and we're left with 22 pi over 15. J, 1 radian, can be converted to degrees by multiplying it by 360 degrees over 2 pi, and we end up getting 180 degrees over pi degrees, which turns out to be approximately 57.3 degrees. Some students will memorize this using the Heinz 57 varieties of ketchup. But it is important to know that 1 radian is approximately 57 degrees. In terms of revolutions, we multiply our 1 times 1 revolution over 2 pi, getting 1 over 2 pi revolutions. Pi revolutions can be thought of in degrees as multiplying the pi revolutions times 360 degrees over 1 revolution, and we get 360 pi degrees. To change to radians, we multiply our pi revolutions times 2 pi over 1 revolution, and we get 2 pi squared radians. Even though an angle of 1 degree is very small, it can be further subdivided. There are 60 minutes in 1 degree and 60 seconds in 1 minute. So we see that 1 degree is equal to 60 minutes, 1 minute is equal to 60 seconds, and therefore 1 degree is equal to 3,600 seconds. To give a sense of how small an angle of 1 minute is, if we were to see a 100-foot tree at an angle of 0 degrees 1 minute out in the distance, that tree would have to be over 6,000 feet away from us, a distance of well over 1 mile. And if the angle was 1 second, then that distance would change to 68.18 miles. Minutes and seconds can make a difference when the radius of the circle is large. We use this type of measuring distances on the face of the Earth, which has a radius of about 4,000 miles. We use lines of latitude and longitude to determine points on the Earth. On the equator, 1 degree is 54.6 miles. 1 minute is 4,800 feet, close to a mile, and 1 second is 80 feet. So, to convert an angle in the form of degrees, minutes, seconds, theta degrees, A minutes, B seconds, to decimal degrees, which would be theta point DDD, just simply use the formula theta plus A over 60 plus B over 3,600 and round to the appropriate number of decimal places. So 37 degrees, 12 minutes, 24 seconds can be calculated as 37 plus 12 over 60 plus 24 over 3,600, which gives 37.207 accurate to 3 decimal places. So converting decimal degrees, theta point DDD degrees, to degrees, minutes, seconds, theta degrees, A minutes, B seconds, is a little bit more involved. We know the theta. To find A, simply take the theta point DDD and subtract theta. That will just give you a decimal. Multiply that by 60 and round to the nearest integer, and that will be the number of minutes. To get the number of seconds, we will use the integer value of our minutes, which is A point DDD minus A. Again, multiply that by 60 and round to the nearest integer. So 28.923 degrees can be changed to degrees, minutes, seconds by taking the decimal part, 0.923, and multiplying it by 60, and we get 55.38. We then take the decimal part of that, 0.38, and multiply it by 60, getting 22.8. Therefore, our 28.923 degrees can be written as 28 degrees, 55 minutes, 23 seconds. The TI 84 or 83 calculator can do this conversion. Degrees and minutes are found in the second angle menu, while seconds are generated by using alpha plus. We don't use seconds that often, but it is available. Converting from decimal degrees to degrees, minutes, seconds can be accomplished using the second angle menu and the arrow DMS command. We see the second angle menu, and notice we use the first 2, and then the 4th. So 37 degrees, 12 minutes, 24 seconds would be typed in using 37, second angle 1, 12, second angle 2, 24, alpha plus. And to 3 decimal places, our answer is 37.207 degrees. Going backwards is a little bit easier. To change 28.923 degrees to degrees, minutes, seconds, we would simply punch in 28.923, second angle 4, and we would get 28 degrees, 55 minutes, 22.8 seconds, which could be rounded to 23 seconds. In exercise 4, you are given 6 angles, 3 in degrees, minutes, seconds, 3 in decimal degrees, and you are to convert the angle to the other form. You can use the formulas that were given or the calculator conversion second angle menu, or in some cases you should be able to do them right in your head. I suggest that you pause the video while you do them and then check the answers. On A and C, there should be no need for calculators. 30 minutes is a half a degree. So 23 degrees, 30 minutes is exactly 23.5 degrees. Same with C. 0.25 degrees is a quarter of a degree, which corresponds to 15 minutes. So 12.25 degrees is the same as 12 degrees, 15 minutes. Notice that in E, 59 degrees, 59 minutes, 59 seconds isn't exactly 60 degrees, but to 3 decimal places, the answer is accurate. We know that the circumference of a circle is given by the formula C is equal to 2 pi r, where r is the radius of the circle. Now realize that the 2 pi in the formula is just the radian measure for a full rotation of the circle, 360 degrees. If we want a fraction of this circumference for the length of an arc, we use the radian measure of the central angle. This formula can be used to find the length of an arc intercepted by some central angle theta. So we have the arc length formula that says S is equal to r theta, where r is measured in linear units and theta is measured in radians and S is measured in linear units. This is a simple formula to use, but realize that when you use it, theta must always be measured in radians. If it is not in radians, you must put it in radians. In number 5, you are asked to find the arc length if the radius of the circle is 4 inches and the angle is 60 degrees, as shown by the figure. Using the arc length formula, S is equal to theta r, or S is equal to r theta, we get that S is equal to 4 inches times 60 degrees times 2 pi over 360 degrees. The degrees cancel, and we are left with 4.189 inches. Please make sure that your answer makes some sort of sense. Students who forget to convert the angle to radians will usually get answers that are far-fetched. Note that in this calculation that we just performed, the degrees canceled out and the only units left were inches. However, technically, since the angle is measured in radians, we would then say that the angle would be 2 pi over 360 degrees radians. Technically, though, r is not measured in inches, but inches per radian. So the calculation would be S is equal to 4 inches per radian times 60 degrees times 2 pi radians over 360 degrees. And everything in terms of units cancels except the inches, and we get 4.189 inches. You don't have to worry about this. Note that when you use the formula, if you use it correctly, whatever r is measured in, s will be measured in the same units as long as you convert the angle to radians. In this case, notice that our central angle 60 degrees is just slightly larger than 57 degrees, which is approximately 1 radian. So in this case, we would expect that S, our arc length, would be slightly greater than the radius. And 4.189 is slightly larger than 4. Our arc length formula, S equals r theta, has 3 variables, S, r, and theta. So if we know 2 of the variables, we can find the other. For instance, in example 6, we are told that the arc length is 6 inches and the radius is 2 inches, and we would like to find the central angle in degrees. It is not necessary to make a drawing, but creating one gives a sense of how large the angle should be. We solve for theta, and that is equal to S over r, giving 6 inches over 2 inches, and that gives 3. However, remember that as we use the formula, if we know theta, we must change it to radians, and if we find theta, it will automatically be in radians. So, since we are asked to find the central angle in degrees, we are going to have to change the radians to degrees. So we multiply the 3 by 360 degrees over 2 pi, and we get 171.887 degrees. And that certainly looks correct when we look at the diagram. A follow-up on angles. Look at this road sign that is seen in Canada announcing distances to cities. The distance to Toronto is 89. It sounds far, but realize that in Canada the metric system is used and the 89 is 89 kilometers. But most Americans don't think in metric, so they need to convert it to miles. A rough estimate is that 10 kilometers is about 6 miles. So 90 kilometers would be about 54 miles. The same is true with angles. Most people don't know what a radian is. So while it is correct to say that the answer to the previous problem is 3 or 3 radians, we generally change that angle to degrees because people are more comfortable using degrees. But remember, to use the arc length formula correctly, the angle must be converted to radians. In example 7, you are told that the arc length is 2 meters and the central angle is 125 degrees, and you're asked to find the radius of the circle. Again, drawing the picture to scale will give you the information that the radius will probably be about half the arc length. We use the formula S equals r theta. Solving for r, we get r is equal to S over theta, and that gives 2 meters over 125 degrees. But again, we must change the degrees to radians. and therefore using the conversion that 360 degrees is the same as 2 pi, we multiply by 360 degrees over 2 pi. The degrees cancel, and we're left with 2 over 2 pi, which turns out to be 0.917 meters. I am a big fan of including units when using formulas, so the cancellation of units is clear. In this problem, technically, since the theta is in the denominator, we change it to radians there, getting 2 meters over 125 degrees, and that is multiplied by 2 pi over 360 degrees. Now, inverting the 2 pi over 360 degrees, we get 360 degrees over 2 pi. We were able to skip this cumbersome step because we knew that we needed degrees upstairs to cancel the degrees downstairs. So for the remainder of this unit, we will be including units in our calculations. In number 8, we're assuming that the Earth is a sphere of radius 4,000 miles. Miami, Florida is at latitude 25 degrees 47 minutes 9 seconds north, while Pittsburgh, Pennsylvania is at 40 degrees 26 minutes 26 seconds north. And the two cities are on the same meridian, which means that one city lies due north of the other. And we would like to find the distance between the cities. Since they are on the same meridian, we can use the arc length formula to do this. Note that to do this problem, the two cities must be due north of each other on the same meridian. If they are not, we need to use spherical geometry to calculate the distance, and that isn't taught for several years. We first need to find the angle between the two cities, and we can do this using the calculator. Punching in 40 degrees, 26 minutes, 26 seconds, we get 40.441 degrees. 25 degrees, 47 minutes, 9 seconds is 25.786 degrees. Subtracting the two, we get 14.655 degrees. However, a much easier way on the calculator is just to input them and let the calculator do the subtraction. 40 degrees, 26 minutes, 26 seconds, minus 25 degrees, 47 minutes, 9 seconds is 14.655. Using our arc length formula, we get S is equal to 4,000 meters times 14.655 degrees. And changing to radians, multiplying by 2 pi over 360, we get S is equal to 1,023 miles approximately. In doing this calculation on the TI calculator, it is important not to punch in the 14.655. If you do that, then any decimal places beyond the 0.655 will be lost. The best way to do this is to do the subtraction and then hit the multiplication sign. The calculator will respond with ANS, which is the previous answer. And even though you may be set to 3 decimal places, the calculator knows that there are more beyond it. You multiply that by 4,000 times 2 pi using the pi button, and then divide by 360 degrees. It may make a difference, it may not, but this is the best technique to use when you are using the calculator. The second part asks us to do the same with Washington, D.C. at 38 degrees 53 minutes 22 seconds north, and Lima, Peru, which is at 12 degrees 2 minutes 47 seconds south. As before, these two cities are on the same meridian. In this case, since Washington is north of the equator and Lima is south of the equator, we have to add the two angles. And when we add them, we get 50.936 degrees. So using our arc length formula, we get S is equal to 4,000 meters times 50.936 degrees times 2 pi over 360 degrees. And we end up with the distance between Washington and Lima is approximately 3,556 miles. Imagine an object that is traveling along a circular arc. We now introduce the element of time to the equation. The object is moving along the arc. Is it moving fast or is it moving slow? In order to do problems in such situations, we need to identify variables that can express certain information. So let's examine the important variables for problems in which an object is moving along a circular arc. We first talk about the variable r, and that represents the radius of our arc in which our object is moving. This is measured in linear units, and when we use it in formulas, it will either be written as linear units or linear units per radian, as we saw in the arc length formula. So some sample measures are 4 inches, or the radius is 1.5 feet. The second variable is theta, and we know that that represents an angle. Angles are measured in degrees, radians, revolutions. However, whenever you use them in our formulas, they must be in radians. So some sample measures of theta are 25 degrees, 1.5 pi radians, or 0.75 revolutions. We next have our variable s, and we know that that represents the arc length. So as our object is moving in a circular pattern, we have the arc length, which will be measured in linear units. When we use them in the formula, they will also be in linear units. And some sample measures are 2.3 feet or 5 centimeters. Next, we have the variable t. T represents time, and that will be given in time units. When we use them in formulas, that will also be in time limits. So some sample measures are 2 seconds or 2.5 hours. Next, we have the variable v, which stands for linear velocity. As our object travels in a circle, it is covering a certain amount of distance per time. So v is measured in linear units over time, or s over t. When we use it in the formula, it will also be in terms of linear units per time. So examples are 5 feet per second, or 12 miles per hour, abbreviated mph. Finally, as our object travels in a circular pattern, it has an angular velocity, and we call this the Greek letter omega. It is represented as an angle over time. Whenever we use it in the formula, it must be in terms of radians per time. So examples are 15 degrees per second, or 8 RPM, which stands for 8 revolutions per minute. In example 9, we are given 6 sentences that deal somehow with a circle, and we are to determine which variable we are being given: r, theta, s, t, v, or omega. If you are told that you are making a U-turn with your car, that means that you are turning the car 180 degrees. and that means that you are being given theta. If you are told that the spoke of a wheel is 5.8 inches, then you are given its radius r. There's an old movie by the name of Around the World in 80 Days. Since we are doing one full rotation of the Earth and we are taking 80 days, this is an example of angular velocity, a certain angle in a certain amount of time, omega. If we are told that we walk 10 minutes along the volcano's circular rim, we are given a measure of time, 10 minutes. This is different than the previous problem around the world in 80 days, where there we were told we did one full revolution in 80 days. Here we are just walking along the volcano's rim. We have no idea whether we complete one revolution of it or a half of revolution, so this is just a measure of time. A circular track measuring 400 feet is telling you S. In reality, it's the circumference, but that is still an arc length of a circle. Being told that a satellite circling the Earth travels at 3,094 miles per hour is an example of linear velocity. It is a certain distance per unit time. Yes, it is circling the Earth, but we don't know whether it's making one full revolution or two full revolutions in a certain amount of time. We're just talking about, in this case, the linear distance that it travels. Quick, change 100 yards into feet. You know you have to work with the number 3 because there are 3 feet in a yard. But do you multiply or do you divide? This problem has bamboozled students for a long time. We now show a method that allows you to easily transform one variable into another. The rule is that you may multiply any variable by the fraction 1. 12 inches over 1 foot is 1, as they both represent the same distance. 5,280 feet over 1 mile is 1. 2 pi radians over 1 revolution is 1. 1 minute over 60 seconds is 1. 1,000 meters over 1 kilometer is 1. So, if we would like to change 100 yards into feet, we will multiply it by 1. And in this case, our 1 is 3 feet over 1 yard, because we want the yards to cancel. And when they do, we are left with 300 feet. In example 10, we are asked to convert a variable using 1 unit to the same variable but using another unit, using the technique that we just showed by multiplying by the number 1. We'd like to convert 15 miles to feet. As stated before, I'm a big fan of putting the units in the actual calculation to show the cancellation. So we multiply our 15 miles by 5,280 feet over 1 mile. The miles cancel and we're left with 79,200 feet. Changing 1 day to seconds is working with time. So we multiply 1 day by 24 hours over 1 day, and then multiply that by 3,600 seconds over 1 hour. The days cancel, the hours cancel, and we're left with seconds. And so the answer is 86,400 seconds in a day. C changes 10,000 degrees to revolutions. This is the variable theta. So we multiply our 10,000 by 1 revolution over 360 degrees. The degrees cancel, and we're left with 27.778 revolutions. D converts 20 feet per second to miles per hour. So we take our 20 feet per second, and first we will work with the distances, and we multiply by 1 mile over 5,280 feet, and the feet will cancel, and we're left with miles. At the same time, we're going to change our seconds to hours, and we realize that there are 3,600 seconds in 1 hour, 60 times 60. So now the seconds cancel, and doing the math, we have 20 times 3,600 over 5,280, getting 13.636 miles per hour. E takes the linear velocity 55 miles per hour and goes backwards to feet per second. So we reverse the process. We start with 55 miles per hour. Again, we will first deal with the distances and use 5,280 feet over 1 mile, and the miles cancel. We then work with the time using 1 hour over 3,600 seconds. Again, the hours cancel. So doing the math, we have 55 times 5280 divided by 3,600, and our answer is 80.667 feet per second. F works with the angular velocity 1 billion degrees per year. And we would like to change that to RPM, which stands for revolutions per minute. So we start with our 1 billion degrees per year. And our first job is to change to revolutions. And therefore, we will multiply by 1 revolution over 360 degrees. The degrees cancel. So we are left with revolutions per year. Now we work with the time. We know that 1 year is 365 days, and therefore the years will cancel. And we also know that 1 day is 24 times 60 minutes. Now the days cancel. So we are left with 1 billion divided by 360 times 365 times 24 times 60. When doing this on the calculator, be careful. You have to take 1 billion and divide it by, and you need to use a parentheses to do the multiplication on the denominator. If you do it right, you will end up with 5.285 revolutions per minute. Suppose we have a duck that is walking along a circular path. We know that in our circle, r is the radius, theta is the central angle, and s represents the arc length. These variables are tied together by the arc length formula, s is equal to theta r, where theta is measured in radians. Now let's watch the duck in motion as it walks about the circle. We still have the relationship s is equal to theta r, but we will now divide both sides by time. And we get s over t is equal to theta over t times r. But s over t is our linear velocity, and theta over t is our angular velocity. So we have the relationship that v is equal to omega r, or solving for omega, omega is equal to v over r. So the duck has two different velocities. It has a linear velocity as it travels, but it also has an angular velocity. and these are related by the formula V equals omega R. Remember, though, that since theta was measured in radians, omega must be measured in radians per unit time. Let us see how the angular to linear velocity formula helps us to solve problems. In 11a, we are told that a bicycle's wheel has a 30-inch diameter, and the wheel, when the bike is moving, makes 1.5 revolutions per second. We would like to find the speed of the bike in miles per hour. This is a simple use of the linear to angular velocity formula. The big challenge here is the changing of units. So we have V equals omega R, and we know that omega is 1.5 revolutions per second. And our R is 15 inches. Our first job is to change the revolutions per second to radians per second. And we do that by multiplying by 2 pi over 1 revolution. Now the revolutions are gone and we are in radians. Now we must change our inches to miles. So we multiply by 1 foot over 12 inches, where the inches will cancel, and then 1 mile over 5,280 feet, and the feet will cancel. Finally, we have to get rid of the seconds and put them in hours, so we use the conversion 3,600 seconds over 1 hour. Doing all the math, upstairs we have 1.5 times 15 times 2 pi times 3,600, and downstairs we have 12 times 5280. Again, make sure if you do this in one fell swoop on the calculator that the 12 times 5280 is in parentheses. And we end up with 8.032 miles per hour. Question B states, a centrifuge has test pilots traveling in a circular path very quickly in order to experience g-forces. If the pilots are traveling at 400 miles per hour and the circular room has a radius of 25 feet, find the number of rotations that the centrifuge makes per second. This problem uses the angular to linear velocity formula, and in this case we know V and R, and we're trying to find omega. So solving for omega, omega is equal to V over R, which is 400 miles per hour over 25 feet. We write this as 400 miles over hours times 1 over 25 feet. We first take care of the miles feet problem by multiplying by 5,280 feet over 1 mile. And those units cancel out, and our answer in this case would be radians per hour. We want our answer in revolutions per second, so we will multiply by 1 rev over 2 pi, and then also multiply by 1 hour over 3,600 seconds. So we have everything canceling out except the revolutions and seconds, and our answer is 3.735 revolutions per second. Again, when you do the calculation on your calculator, you are multiplying 400 times 5,280 over parentheses 25 times 2 pi times 3,600. Problem C states that a large clock has its second hand traveling at 2.5 inches per second, and we would like to find the length of the second hand. Clocks this large are usually garden clocks. There's a famous one in Niagara Falls that is shown here. In this case, we want to find the length of the second hand, which is the radius. And we use our angular to linear velocity formula to get that the radius is equal to v over omega. Doesn't look like we have enough information to do the problem, but we do. We know that v is 2.5 inches per second. And since it's a second hand, we know that a second hand does 1 revolution in a minute. So doing an inversion of the denominator, we get 2.5 inches over seconds times 1 minute over 1 revolution. We then take care of the revolution problem, and we multiply by 1 revolution over 2 pi. Taking care of the time units, we multiply by 60 seconds over 1 minute, and everything cancels out except the inches. So our answer is 23.873 inches. Our last problem, D, states that 2 gears are connected by a belt. The large gear has a radius of 6 inches, while the small gear has a radius of 3 inches. If a point on the small gear travels at 16 RPM, find the angular velocity of the large gear. This problem looks difficult, but in reality is quite easy. Examine the picture. The small gear is driven at angular velocity 16 RPM. Since the belt is attached to it, the belt will have a linear velocity. But this same belt is also connected to the large gear, which has its own angular velocity. So we can set up 2 equations. V equals omega s rs and V equals omega L RL. Realizing that the velocity V is the same, we can say omega SRS is equal to omega L RL. And plugging in the given information, omega S is 16 and the radius of the small gear is 3. The R of the large gear is 6, and we do not know the omega of the large gear. So we get 16 times 3 equals 6 omega L, and therefore omega L is equal to 8 RPM.